We'll continue today chapter 6 and try to do some problems on measurements together. So first, we introduced last time go and no-go gauges. This is an example of snap gauge, which is used to measure diameters of ports. So here, as you can see, if you have a ball and you want to measure what is the diameter of the ball, you can just insert it into your snap gauge, and then you will have several snap gauges, and each one will have a certain. For example, here I can just put that for the go gauge, for example, it's, let's say, 20 point, for example, 5 centimeter. For example, you can have different sizes, and then here it can be, for example, for the no-go gauge, it will be, let's say, 20.549, for example. So in this case, what will happen is that you have several snap gauges. You will try different ones until your ball will go through the go gauge, but not through the no-go gauge. Then you can say that the diameter of this ball is between these two values. Okay, so then, for example, here, let's say the accuracy will be 0.001 millimeter. Okay, now we have also devices to measure angles. This is an example. This is a bevel protractor with a vernier scale. Also in the videos I posted for you in the YouTube links, you have several YouTube links for videos. You have how these devices can work. So this is the bevel protractor that can measure angles. You can measure angles from 0 to 90 and angles larger than 90. So depending on the mode of operation, depending on the angle, you can you will be able to read its value. So it will go from 0 to 180 degrees. Now concerning surfaces, now we'll talk a little bit about surfaces properties. We'll define what is surface roughness, what is surface integrity, and what are the different processes that will alter surfaces. So first, for the case of nominal surfaces, as a designer will just draw contours that are perfect. He will define lines in engineering drawings, so everything is exact. You have, for example, pure parallelism between your lines. You have exact roundness, etc. And you don't take into account any, if you want, error in manufacturing. However, we always know that when we want to design, when we want to fabricate the product, when we want to manufacture it, we'll always have some errors. We should be aware of these errors, and we should set what are the maximum errors allowed depending on the application we are using. So so as we said, nominal surfaces will appear as absolutely straight lines, ideal circles, round holes, and other edges and surfaces that are geometrically perfect. However, actual surfaces are determined by the manufacturing processes that will be used to make them, and will have a variety of processes that can result in wide variations in surface characteristics. So if you desire to have a very good accuracy, you need to go under several processes until reaching the final product you want. Now, surfaces are very important for several reasons. First, for aesthetic reasons, for safety factors. So sometimes in certain applications, we don't allow rough surfaces. We need to maintain a certain contact between surfaces. This is an example. You have friction and wear will depend on the surface characteristics. So if we have an application where we need to use the tool for a long lifetime, we should make sure that it is able to resist friction and wear, and this will be depending on the surface characteristics Also, the surfaces will affect the mechanical and physical properties of the material. We'll see how. And the assembly of parts will be affected a lot by their surfaces. So whenever you want to go to the assembly process, you need to have a perfect match, as much as possible between your surfaces to have a good assembly and have your final product. Now, also smooth surfaces play an important role in electrical contacts. It can be of very high, you should maintain sometimes very high accuracy of smoothness in order to ensure a good electrical contact and conductivity between your different surfaces. So in such applications, you need to go through several processes to make sure that the smoothness of your surface is at the level desired. Now, we'll talk about surface roughness and surface finish. Sometimes, as we said, you need to ensure as much smoothness as possible, like for electrical applications, for surfaces that should be in perfect contact, etc. But now also some other applications require surface roughness. This is why you should have several manufacturing processes allowing you to ensure a wide range of roughness values. Now we'll define what is the roughness. The surface roughness is a measurable characteristic based on roughness deviations. So it will measure deviations from a certain constant value. And surface finish is a more subjective term denoting the smoothness and general quality of a surface. So we say when we have a very good finish, this means in general that the surface is very smooth. And in popular usage, surface finish is often used as a synonym for surface roughness. And both terms are within the scope of surface texture. So when we talk about surface texture, we just talk about, if you want, the external surface. Okay, we don't take the layer below it. We'll see after that surface integrity will consider also the layer below the top surface and how its property can affect the material. So first, in order to measure surface roughness, we have here an example. So let's say we have a certain value. We need to have a flat surface, for example, and we want to test after manufacturing it how much it's close to the surface desired. We can measure then the deviations in the upper and lower parts. So we'll take the absolute values of deviations, okay? Because, for example, here, if you do the average value without taking the absolute value, it might be confusing because you have zones that you have a deviation upward and other zones that where the deviation is downward. So it's just do an average value, you might get a value close to zero, while in reality you have deviations. This is why when calculating, if you want the average deviation, we take the absolute value of deviation in order to consider the possibility of having deviation from the upper side or from the lower side. Now, we have several ways to measure the roughness of a surface. The first method is by integration, and this will give you an accurate value of roughness because you integrate over your whole length. So this is called the arithmetic average, which is based on the absolute values of deviations. We already said why we take the absolute values to not have, if you want, to not have positive regions canceling out other negative regions. And so all you have to do is when you consider a certain length of your specimen, you measure at each position what is the deviation, and you can get a function for your deviation. And then you integrate this function over the total length, dx, to get the average value of your roughness. Now, sometimes it's hard maybe to, in order to generate this profile, you need sophisticated equipment. We'll see what is the equipment that can allow you to draw the roughness profile. but also will define another easier method. Maybe it's little less accurate, but will not require to have the complete profile. What we can do is, instead of drawing the complete profile of roughness, we can take a certain high number of points on the specimen and measure the deviations from the nominal value. And then we can define roughness as a summation for the points of the absolute value of deviation over the number of points considered. Okay, of course, higher the number of points, better is the estimation of your roughness, and it will be then close to the integral calculation. Please interrupt me if you have any question. Now, concerning, we talked already about surface texture. Now we'll deal with surface integrity. And as I told you, the surface texture will just observe the external profile of your surface without going deep into your product. However, for integrity, it will consider the layer that is below the top, and it will study its characteristics. We'll see that this layer can have a large effect on the mechanical properties of the product. So as we said, surface texture alone does not completely describe the surface. We should also consider what is happening below the top surface. So there may be metallurgical changes in the altered layer beneath the surface that can have a significant effect on a material's mechanical properties. We'll take together several examples how the characteristics of this layer can be an indication about some manufacturing processes that were used to get our final product. Surface integrity will be the study and control of the subsurface layer and the changes in it that occur during processing, which may influence the performance of the finished part and product. So now we'll talk about several processes that will affect the surface integrity. So let us see what are surface changes that can be caused by processing. So surface changes are caused by the application of variable forms of energy during processing. So for example, you know that mechanical energy is one of the most forms used in manufacturing, and it can lead to the formation of your object to reach the final desired shape. And these processes will include forging, extrusion, and machining. We will talk in detail in future chapters about these processes. Now, although its primary function will be to change the geometry of the work part, but when doing these processes, the mechanical energy will also cause some residual stresses. If you remember when we studied the deformation, the variation of stress with epsilon, if you remember, we said that if we exceed the elastic region and then we release the stress at a certain level in the plastic region, it's just the material cannot go to the initial state. So we'll have a permanent deformation. We'll have what we call residual stresses. So sometimes we have residual stresses that are desired, and sometimes they are not, depending on the application. We talked also about strain hardening. So how this can affect the mechanical properties of your material. And sometimes we can, due to deformation, and we might lead to cracks in the surface layers. Cracks in general are a weakness sign, and we try to avoid them. Okay. So here we have several energy forms other than the mechanical energy that can affect the surface integrity. Already for mechanical energy, we talked about the example of strain hardening and residual stresses. For thermal energy, you can have also an effect on the surface. We already introduced together the concept of recrystallization, and we have seen how recrystallization will lead to the formation of new grains, if you remember, and this will allow easier deformation of your material. So in that way, of course, if we look at the sublayer, we'll see a change in form, and due to the application of thermal energy. Another application here is heat affected zone. What we mean by the heat affected zone, it's a non-melted area of metals that has undergone changes in material properties as a result of being exposed to high temperatures. We can take the example of welding or high heat cutting. So if you are welding objects, okay, together, so you have first what you do is you expose this zone to very large temperatures, and you will have a certain if you want melted metals that will be introduced in order, and then you cool it in order to weld the two parts. But due to this process, what will happen is that you will have a formation of zone here that is affected by the high temperatures that the product was exposed to, and therefore the properties of this part will be different than the remaining parts, okay, due to this heated treatment. So this is how sometimes thermal, this is an example of how thermal energy can affect the surface integrity. Other types is the chemical energy. So you know that you can have, due to chemical reactions, you can have corrosion, you can have contamination, etching process, and also for another type of energy that can affect surface integrity is the electrical energy, where you can observe in the sublayer a certain change in conductivity or magnetism property due to application of electrical energy. So we have several forms of energy that can affect the surface integrity. Now, how to do measurements on surfaces? So first, the first parameter of interest is the surface texture, and this is easier if you want to measure than the surface integrity. You can just study the geometry of the surface, and this commonly measured as the surface roughness. Now we'll see what are the equipment that will be used for this purpose. Now, for surface integrity, it will deal with the material characteristics immediately beneath the surface and the changes to the subsurface that will result from the processes that created it. So, as we said, we'll study the properties of the sublayers. This is more complex than studying the geometry, of course. We need to test, if you want, the properties. We need to test how the energy forms applied on the surface affected the sublayer. Now, concerning how to measure surface roughness, we have several methods. We have some that are relatively simple but not very accurate, and we have much more complex devices that can be used. So we have first subjective comparison with standard test surfaces. This is not a very accurate procedure, but it will rely on fingernail tests. So what they do, for example, they give you a already tested surfaces with high accuracy equipment, and they put on them what is the surface roughness. So let me show you in the next slide. You have a figure. So here, for example, okay, you have a set of surfaces already studied, and you have for each surface, for example, here's the smoothness, for example, is 1 micrometer. Here it is. So you have a set of roughnesses already measured before, and you will rely on comparing the touch of these surfaces with the surface of interest. And when you see that you have a comparable roughness, you can say that I can say that the roughness of the surface is equal to this one. This is called a subjective method of measurement because it's not very accurate. Sometimes you might feel that the roughness is very close, but especially if you have very small values, it will be critical to use this method. So maybe for larger roughness, it can work a little bit better. Okay. This is why when we have very small roughness, we can go to more advanced techniques. So you have the fingernail. We talked about the fingernail test as the first method, which is a subjective comparison. Second method, which is much more accurate, is the stylus electronic instrument. And we have also the optical techniques. We'll see them in details. So as we said, for the first method, you have a set of surfaces already tested, and you try to compare roughness by a fingernail test. This might be, as we said, critical for small roughness. This is why we develop other techniques that are more accurate. For the stylus instrument, it is, if you want, similar in concept to the fingernail test, but it's not done by humans. So it's an electronic device that will transform the motion of a stylus to a function showing the variation of roughness. We'll see how. So in these electronic devices, the idea is you have a cone-shaped diamond stylus that will traverse the test surface at slow speed. And as the stylus head is traversed horizontally, it will also move vertically due to deviations, okay? And this motion, the motion of the stylus in the vertical direction, will be converted into an electronic signal that can be displayed as the profile of the actual roughness. Okay, it will show you deviation, so how you are deviating from the nominal value. And then it can be used to measure, as we have seen together by integration, the average roughness value. So this is an illustration of this stylus instrument. So as you can see, this is a stylus, okay? It will be in contact with your surface. You move it horizontally, slowly, so that it can capture if you want the deviations. If you don't have any deviation, which is not really possible, it will not do any vertical motion. So you will just have horizontal motion. However, whenever you have a deviation from the nominal size, your stylus will move up and down, up and down. And this motion will be transmitted electronically to be converted to a profile, how the motion, how your stylus is moving. And this will be represented by a signal, by a profile, okay, on a computer. And then you can determine the profile of roughness and measure it using the integral procedure. So this is a stylus instrument shown, used in an important university in labs. So here is a sketch of how this equipment is working. So this is your stylus. It's moving in the horizontal direction. And as it's moved in the horizontal direction, because of the roughness of the surface, it will move up and down. And this vertical motion will be transmitted, and it will be due to an electrical signal. It can be drawn by a computer. Now, other techniques will consist on you have in this case 3D techniques that can use a microscope with a digital camera and a motorized table. So this is also much more complex. It can be used in 3D applications, and that can give you a roughness of a certain surface, and also it can draw for you a map of the 3D surface. Okay. So I think you might see in your manufacturing lab some of these devices. Now, concerning tolerances and manufacturing processes, we already talked that depending on the application, tolerance can change. Sometimes for a certain product, let's say you are just doing a sand casting process to have a certain profile, to have, let's say, for decorative purpose, you might allow here some error. It's fine for you. However, if you have, let's say, an electronic device and you want to ensure very smooth surfaces, it will be much critical to have an accurate machining process. So manufacturing processes are very widely in accuracy. Most machining processes are quite accurate, and they are capable of tolerances up to plus or minus 0.05 millimeter or better. And more your tolerance is small, then you need to go over a series of machining processes, one after the other, to if you want to be close to your final desired shape at the end. Now, for example, we'll see in next chapter solidification processes. One of the most used solidification processes is sand casting, but it's one of the most inaccurate processes, and tolerances in this case is 10 to 20 times higher than those used for machine parts. So as I told you, it depends on your application. If you just have decorative objects, it's fine for you. So here, if you multiply by 10, for example, it's 0.5 millimeter. It's okay if you just want to produce something for a decorative purpose. It's fine if you have it all, if you have an error of 0.5 millimeter. It's not the end of the world. It's, you will not even notice this on the macro scale. However, for other applications where smoothness of surface is critical, then you cannot use you can use, for example, sand casting as a first process, but your product will undergo several other machining processes until reaching the desired accuracy. Now we have processes that are capable of producing better surfaces than other. So we have here, we talk about several processes and we'll see some details about them. In general, processing cost will increase with improvement in surface finish because additional operation and more time will be usually required to obtain increasingly better surfaces. We have several processes that are noted for providing superior finishes, including a honing process, lapping, polishing, and super finishing. For example, when we talk about honing process, in honing process, we use a special tool, which is called a honing stone, okay, to achieve a precision surface. Then the honing will be composed of abrasive grains that are bounded together with an adhesive. And by doing, if you want, مثل ما نحف السيرفيسز على بعض بنحف الستون which is characterized by if you want high very small grains. هي الفكرة انه when you have very small grains on it of the order of 10 to 50 micrometers بس تحفوه على surface, this will smoothen your this will lead to reduction of the roughness of your surface. Okay, so and more the grains used for the honing stone are smaller, you can reach a better smoothness for your surface. Now, for example, when we talk about lapping, lapping is a machining process in which two surfaces are rubbed together with an abrasive between them. And we can have, if you want, relative motion between the surface or by hand or by using a machine. Of course, currently everything is transformed to machines because it will be much accurate and much faster. I encourage you, please, to go over the YouTube videos that they will help you to see in reality how this is taking place. For each chapter on Blackboard, I posted for you several links illustrating all concepts we are talking in the chapter. In this chapter, you will find videos about measurement devices, how we use vernier scale, what are the different processes that will alter surfaces. So we talked already about, for example, honing, lapping. You can see them in reality, how these processes take place. So it will be very good to watch these videos. They can help you to imagine the situation and that will facilitate studying on you after. Okay, so please go over them, and they are interesting, and you can see in practical cases how these processes are done in industries. Now for polishing. Polishing is the process of creating a smooth and shiny surface by rubbing it or using a chemical action, leaving a surface with a significant specular reflection. And super finishing, okay, this is one of the most accurate processes, as the name indicates. So it will lead to a very good finish of your surface. And in general, it's the last process used to lead to a very high smoothness of your surface. So super finishing is also known as micro machining or micro finishing, and it will consist on improving the surface finish of your workpiece geometry. Okay, so this is chapter 6. please, as I told you, go over the videos. They are interesting and can help you to understand better these concepts. Now, I will start with you problems on vernier scales. We talked in brief about vernier scale last time. And now I will go over a file that is posted for you on Blackboard in assignments. In assignments, you have a file that is designed to show you first how vernier scale work and how we can read measurements on a vernier scale. Okay, so we have talked before that vernier scales are used to increase the accuracy of measurements, and the precision of length measurement can be increased by using a device that uses a sliding vernier scale. Now we have several types of vernier scales. We have linear one, and we have rotary vernier scales. We'll see how in this file. So such instruments are based on a vernier scale, which you will use in the labs to measure lengths of objects, and we'll see how they operate. You have different range of accuracies depending on what is your main scale and what is how many divisions you have in your vernier scale. Let us start with some examples to see how we use these vernier scales. We'll start first with the sliding vernier scale. So for example, if you look in the figure below, okay, you have two scales. This is the main scale. So this is the main one. And you will have an annotation here, for example, that your readings on the main scale are in millimeter. And then this is the vernier scale. And the vernier scale will divide each millimeter into several parts. Okay, so here your accuracy of reading in the main scale is 1 millimeter. However, when you use the vernier scale, your accuracy will increase to 0.1 millimeter, because here you have 10 divisions. If you have, for example, 20 divisions on your vernier scale, the accuracy will be of the order of 0.05 millimeter. So higher the number of divisions on vernier scale, better will be the accuracy. So this is if we have 20 division. If we have 10 divisions, as the case here, we have 10 divisions of 1 millimeter, then the accuracy of reading will be up to 0.1 millimeter. Now, how it's working, how the vernier scale is working. First, you look at, if you want, if you read here on the main scale, okay, you look at your 0. So the zero of your vernier scale is just at this level. So you have 3, you have division, you count your divisions, 1, 2, 3. So I am reading from the main scale 3 millimeter, and I will read from vernier scale, okay, what is this number after the decimal. So it's 3 point what. To determine it's 3 point what, I will go to my vernier scale now and look at the perfect match line between the vernier scale and the main scale. What do I mean by this? If you look here at this line 0, okay, it's deviating from this one, so no match. Also for 1, it's not matching any of these two lines. So you continue, 2 is not matching, 3 is not. You can see that here the lines are coming close to each other, but still no perfect match. The perfect match is here. If you look at the line of the main scale and the line of the vernier scale, they are collinear. Okay, so they are coincident here. This is why we say that we are reading here 0.7 millimeter. So in total, your reading is 3.7 millimeter. Okay, so in summary, here you have the summary of the method. So in the figure below, the main scale reading is the first reading on the main scale immediately to the left of the 0 of vernier scale, which was 3 millimeter. while the vernier scale reading is the mark on the vernier scale which exactly coincides with a mark on the main scale, which is 0.7 millimeter. And therefore, the total reading is 3.7 millimeters. Let us take another example. If you take the following figure, okay. So again, here they should specify for you the scale. For the main one, it's in millimeter. And then you have 10, 11, 12, 13, 14, 15 to the left of 0. Yani always you look at 0 of your vernier scale. To the left of it, the first graduation corresponds to 15 millimeter. So I'm reading from the main scale 15 millimeter. Now I should read after the decimal what is the measurement. I look at the vernier scale and I try to identify where I have a perfect alignment of my graduations. It's not 1, not 2, not 3, not 4, not 5, not 6. 7 is little, it's very close, but the perfect match is at 8. Okay, so you see that 7 is very close, 9 is very close, but 8 is the perfect match. So I can read here 15.8 millimeters. Any question on how we do the readings for vernier scale? Okay. Now, let us see actual devices with more divisions, okay? So as I told you, always the number of divisions will affect the accuracy. Higher the number of divisions you have, larger will be your accuracy, okay? For example, here, if you look at the main scale as usual is divided into, so I can read here, for example, it's in centimeter, okay? So the main scale is in centimeter, and then each, so when I have 3, it's 3 centimeter, 4 centimeter, 5 centimeter, etc. And each centimeter is divided into the main scale into 10 parts. So I am able to read up to 1 millimeter in my main scale. Okay, so this is the accuracy is up to 1 millimeter in my main scale. Now, if I look at my vernier scale, this is 0. This is my 0. Okay. Now, the first strategy is to look at to left of 0. What is the value I read? It's here. So if I count, I have 31, 32, 33, 34, 35, 36, 37 millimeter, or 3.7 centimeter. So I can read here 3.7 centimeters, or which is corresponding to 37 millimeters. And now, if I look at my vernier scale here, it is divided into 50 divisions. Because if you look, you have from 1 to 10 as big divisions, but each division is divided into 5 smaller divisions. So here, this corresponds to 0.1 millimeter. Okay, but this 0.1 millimeter is divided into 5 parts: 1, 2, 3, 4, and 5. This means that each part will represent 0.1 over 5. So it's 0.02 millimeters. So the accuracy of my vernier scale is of the order of 0.02 millimeter. Okay. And in total, then, my vernier scale is divided into 50 divisions. I divided first into 10 big divisions, and each of these 10 is divided into 5. So in total, I have 50 divisions. This